I want to point out that this talk with my son is available online on the archive and will be in AppJ within a short time, I hope. I gave you a teaser about this yesterday, so to speak, but I want to get to the main message. You'll be glad to say there are no complex slides here. I start back with this graph I made up of all the major ways to get to higher speeds, and as you can see, the only way to really get to high speeds that's practical are the beam-driven sails for us now, because for one thing, the Benford ramjets turn out, we happen to be in a bubble, and there's just not enough fuel to make the ramjets sensible. So there are also mechanical issues that came up were studied in the 20th centuries about interstellar ramjets, but those have been largely resolved. Now, here's the thesis. The most conspicuous observable feature of an advanced ET civilization may well be, and I think will probably be, the leakage of large-scale beaming of electromagnetic power over planetary, interplanetary, and interstellar distances, because that moving power around with beams is a very efficient thing to do. Why? Well, photons don't suffer energy losses in gravitational wells, except for negligible gravitational shifts. And they can be provided with efficiency and economy. The consequence of that, you'll see, is that the SETI messages may well be found on power beaming leakage. That power beaming leakage is more powerful than any beacon we're likely to ever build, and it would be done for economic reasons, which has its own drivers, and therefore we ought to be looking at the transient signals, many of which we've already seen, and seeing whether or not there's a message embedded on them. I'm going to, what I've done is a study of all the proposed power beaming missions, quantified them. I haven't got time here to describe them in detail. I'm just going to show you pretty pictures. But they are basically launch into orbit, orbit raising, interplanetary commerce, which John Guyon will speak about after me in a very good piece of work, the interstellar precursors, and then starships. This is Kevin Parkin's invention, the microwave thermal rocket concept. It's to get up into orbit driven by microwaves and essentially about 1 or 2 ton vehicles carrying cargo. The next level of mission is to boost from that orbit up to higher orbits using beamers that are either on the ground or in orbit. And my brother's done some studies about this at UC Irvine and shown that by resonant boosting, you can get really very efficient and fast boosts into upper orbits. This is the least power requirement of any of the missions I'm talking about. I shouldn't say missions, I should say applications. And then there's interplanetary commerce, which I will let James talk about. And basically you have something, in this case, you've got a beamer in orbit, hitting a sail, accelerating it up to high speeds and getting off towards, say, Mars or the moons of Jupiter. And then, of course, there is the interstellar precursor, which you've got to get up to hundreds of kilometers a second to be able to do it on the lifetime of an interested astronomer. And so that domain requires ever higher energies. And then, of course, we get to Bob Ford's Star Wisp, a microwave-driven sail in which the electronics are integrated into the sail. It's a very smart device. And so it can correctly configure itself to, say, beam energy information back to us. And then sail ships of this kind of a concept, which we saw earlier today. By the way, these graphics, I commissioned Adrian Mann to draw all of these, and I've allowed them to be publicly distributed. I have dozens of them from different points of view, if anybody wants them. Now, down to the numbers. Well, that is one way of looking at this graphic I showed you yesterday. There are domains of applications which show that as you go up higher and higher in energy requirements, you get to different classes of missions and higher power and generally longer duration as you go up through them. Now, this is the graphic I showed you yesterday. And here, you see that on the diagonal is the lines of constant energy, and the you go from a launch to orbit to interplanetary to interstellar. These missions, these applications are all quantified in these 20, about 24 really, studies done. The studies are not optimized for cost. They are not internally consistent, but they can be made so, and I intend to do that in the near future, so that those points may move around a little, but we've made this into domains because, in fact, the numbers tell a story, but the domains are really what we should think about. And what it says is, in the next slide, if you look at the Arecibo transmissions, the planetary radars, and other radars we've used, that's down at this kind of a power level on the left. Then there are the beacons that my brother and my son and I have quantified, which are cost optimized and probably the cheapest beacon you could build, and shorter pulses, by the way, and operated repetitively so they can be seen easily, over on the left. And then there's Starshot. Now Starshot's an interstellar mission. It's not up there with the other interstellar missions because it has such a small mass. If you can't get Starshot down to a smaller mass, then it's going to move upward toward upward to the right. The point is that these are more highly observable than any beacon anyone's likely to build. And beacons actually don't have a commercial application. At least I'm pretty sure they don't. Now, the key thing through the next few slides is to look at what are the parameters these mission studies, these applications give us for what the observables will be. The title of this talk really is Power Beaming Leakage as a SETI Observable. Notice I'm talking about what leaks around the sail as an observable, because there's always going to be leakage. And you can see that the frequencies over these studies varies through the microwave to the millimeter up to into the lasers. The power levels go over many orders of magnitude. This is just a sampling of the numbers. You can see the paper for some detailed numbers. And I can distribute a spreadsheet that contains all the numbers for those who are interested. The duration varies from minutes to hours to years. I mean, there's a big variation in missions, because driven by the fact that there are big variations in energy. Now, the repeat time depends exactly on what the mission parameter is. The launch to orbit has to take place in minutes, and orbit raising can be done in hours or slower, and therefore interplanetary, of course, the beaming part can be done in hours, and then there's a coast and it slows down at the other end, as James will show you after me. The repeat time is, again, debatable and covered in detail in the paper, but they're typically, the launch scenarios into orbit are you fire it and you fire it, you launch and launch and launch, because you want to use the time your range is open and when the windows of opportunity for orbiting are there. So you see there's tremendous variation in the repeat time as well, and so that means you have to really watch and wait. But you may see them come in a series of bursts, or let's say bursts over a single day or so. The beam width in radians varies from on the order of 10 microradians to very small in micro arc seconds, 4 micro arc seconds. And they're pretty narrow, and therefore that gives us an EIRP, an effective isotropic power. And I want to point out also another key parameter is the fact that there has a beam width that I just mentioned, but also a slew rate as the beam moves to follow its target and accelerate it. And that leaves us then to an EIRP, which is simply the product of the power and the gain, which is watts in a per steradian. And that quantity, which I call W, relates to the power density you would receive here and the range you would have to estimate to the signal you're receiving. So given the power density you measure and the estimate of the range, you can calculate the EIRP, and the result of that is shown in this slide. I give here the slew rates for various launches. for various applications, which can vary from fairly slow, radians in second, down to very, very slow. They're not moving very fast. The EIRPs vary from 10 to the 19th to 10 to the 38th. Let me point out the EIRP of the Arecibo radar is about 5 times 10 to the 13th, and therefore, as you can see, these are far more luminous emissions than anything we have done. The time that you would be seeing it over is the beam width divided by the slew rate, and that varies from a fraction of a second to a few seconds to very long if you should happen to see the beam of a starship. I should point out that you won't see the beam of the starship usually because it will lead the target, the star it's going to. If it was coming toward us, we wouldn't see the beam. It would be shooting ahead of us. And you can see that as a ratio of speeds in the paper. Now, observations by Jerry Harp and the people at the Allen Array have been made toward looking at that anomalous star called Tabby star, with the concept that it might be a Dyson cloud or some other astroengineering taking place because of these unusual signatures that have been observed and are still, to my knowledge, still unexplained. A total mystery. They did observations. I'm going to compare their observations to these applications and see what they say, what they tell us about it, of their observations. Now, they worked in the 1 to 10 gigahertz regime, in 1 hertz channels and in a moderate band 100 kilohertz channel with different EIRPs for sensitivities for the 2 different channels. And the observations took place over 2 weeks, observing half the time. And here's the implication in terms of these applications, these missions, of those observations. First, the 1 hertz channel could see all of these applications, but they are not seen. A launch from planetary surface into orbits, marginally detectable, not seen. Orbit raising, not detectable in these observations. Interplanetary transfers, detectable, not seen, of course. And that's true of both bands. Starships are not seen, but should not be seen unless it's some kind of very lucky side lobe that we're seeing, not a side lobe, but we're seeing a main lobe that's launching toward a star that's the destination, some other star is the destination. So, but there are caveats about this. Power beaming is not an isotropic endeavor. It's very directed, and so the geometry may not be right, and so not seeing something doesn't mean it isn't there. It's just not looking at you. The observations were conducted only a limited amount of time. More time would provide a more stringent constraint. The optimal frequencies will probably be higher to keep the aperture size down of the radiator. And so if we look forward toward thinking about measuring directed energy transmissions as leakage, then here are some remarks. First of all, I want to emphasize again, they would dwarf any ETI civilization's routine leakage such as we have. The leakage we have from microwaves is really essentially undetectable very far from Earth. And that's true in the optical as well. The more extensive observations should be made if you want to really try to look for these, but it should be done at higher frequencies, and I show a group of bands here in our atmosphere. And of course, these are transient sources which require staring, and a promising avenue for research in this area is to actually revisit the many thousands of transients which have been observed and are in the SETI at home database, and seeing if there's anything we can gain from that. And I'll get back to that in a moment. Just to point out the atmospheric windows, which I think we all know. There's the radio window, a number of microwave windows at higher frequencies, and then ultimately the visible window in the visible, obviously. And those are the places we should start to look, I think, if we want to look for leakage radiation. Now, the other implications are this. ET would know that the power beams could be observed. I mean, we've already thought of it, and we're not even doing beaming yet. They could put a message on the power beam and broadcast it to our receipt by modulations of various kinds. We may find a message on such a beam. And in future, if we do power beaming, we could put a message on such beams as well. But then we would have to address the METI issue, which I think we should all talk about and have a position about before we get to making any decision. So those are my main points. I want to point out you can see the rather detailed paper online already and later on in AppJ. Thank you.
Thank you, Jim, and I should warn the audience that there are 3 Benfords, and one of whom is your
There are
son.
3 in the sciences.
In this business of space, maybe you should
I have 5
elaborate.
grandchildren, right?
Yeah, so...
Well, one of them's here, Gregory, and the other's my son, who's busy working on W1st at NASA headquarters.
And even though they are identical twins, they have different thoughts, actually, different expertise.
Yes.
Questions? Blakesley.
It seems there's an obvious place to look for this leaked beaming radiation, and that's on the gravitational lens line towards different stars. So, I mean, it's highly beamed, so that makes it difficult to observe, but that's where we're planning to send our laser sails, where we would show signatures of leakage. And therefore, it's maybe not so outlandish to think that that's where we should be looking for these signals as well. I don't know if you have a comment.
Let me make sure I understand your comment. You're saying that ET would be launching something out to their gravitational lens in order to watch things. To know where that point is, we'd have to know, of course, where they're going to look. If they were looking toward us, we wouldn't see it at all, because it'd be on the other side of the star. Oh well, yes, and you would pick that up. That would be a specific form of leakage, a specific mission. Yes, no one I think has really done a power beaming mission analysis to 50 AU and beyond, not to my knowledge.
I should point out that my son is a classical archaeologist at the University of Georgia, and therefore there are 4 of us.
There qualifies as a science, yes.
Yeah, but we were talking about space science. No?
No, still it's an observational science.
Go ahead, Jill.
You mentioned your closing comment about METI and having the conversation, and Creon Levitt yesterday went looking for that democracy application that I said might allow us to have the conversation. He told me I said it was called liquid freedom. It's actually called liquid feedback. So if anybody wants to take that a bit farther, make that correction. Well, when you see the group from Germany that it came from, you could understand why I might have said that.
Okay. One more question?
Jim, for pick an application, let's say terrestrial launch or orbit raising, you mentioned the repeat time scale, but I think the repeat time scale you talked about there was from their point of view, how often or how quickly you might perform the same event. Mm-hmm. Have you thought about, and you must have, let's say for launch, if they were launching from the surface, had a timetable for launches, they were going to do it every day at 3 in the afternoon or something like that, how long it might be for us to see a repeated signal just because of the rotation of some classes of planet in their orbit in their solar system and that sort of thing?
First of all, the time it would take to launch into orbit depends upon the depth of the gravitational well, but that's pretty much like, if it's a rocket, it's pretty much like the depth of our well for reasons having to do with rockets, which we can discuss, maybe a factor of 2, and that's minutes. When they would repeat would depend on how fast they could put together another vehicle to launch, because they probably have a launch window. Right. And also have orbits to consider. Now, on orbit raising, the general what turns out is that you repeat, it comes around, it goes down to the bottom of its orbit. When it comes up, you accelerate it upward. Well, actually, you accelerate it at the bottom of its orbit, the Oberth maneuver. And then when it comes around again, you do it again. You come around again, you do it again, and you get higher and higher in each orbit. And therefore, it's essentially an orbital timescale which stretches out as the orbit gets higher and longer. And the early work was done by Bill Brown on this 20 years ago, and more recent work by my brother and his students in 5 years ago.
Last question, very quickly.
Quick point. You're
Hi, Joe.
proposing that we should look in these windows in our atmosphere, which makes a lot of sense because that's where the telescopes are on the ground. They have to look through the atmosphere. However, have you thought about other atmospheres and other exoplanets and where those windows might appear, and exoplanet people may know what is how?
Yeah.
We
We looked into that. We looked into that. Yes, other atmospheres, other windows. We tried to look up the literature on it, and we refer to that search in the paper.